In this video, I'm going to show you how to calculate the packing efficiency for a face-centered, whoops, this is why I'm not a spelling teacher, packing efficiency of a face-centered cubic metal. Packing efficiency of a face-centered cubic metal. Now, in order for us to try and tackle this problem, we need, of course, to know what packing efficiency means. Packing efficiency is the volume of atoms, right, the number of atoms that are in a particular unit cell, divided by the volume of the unit cell itself. Okay, so what we're doing here is we're trying to come up with how much of the unit cell, what percentage of the overall unit cell is full of atoms. How much stuff can we pack into this space? Multiply this number by 100% and we get our packing efficiency. Different kinds of unit cells are going to have different kinds of packing efficiencies. And it's important that we learn how to calculate this, not just because it can be useful when we go forward in our chemistry careers, but also because getting a familiarity with working with unit cells will be helpful when we start calculating things like density of different crystalline solids. So let's start out with trying to tackle this problem, the packing efficiency of this face-centered cubic metal. Now, in order to come up with this first number here, we'll do this number in the numerator first. In order to come up with the volume of the atoms, we need to know how many atoms it is that we're talking about. A face-centered cubic cell, cubic unit cell, has 6 half atoms. These are the atoms that are bisected down the middle and they're halfway in and halfway out. And 8 1/8 atoms. These are the atoms that are on the corners. So we get 4 atoms total are in a face-centered cubic unit cell. Great. Now, when we go from number of atoms to volume of atoms, we need to come up with some expression for volume. We are going to treat these atoms like they are spheres. The volume of a sphere, if you'll recall, is 4/3 pi r cubed. Now, you might remember this from high school, and that's great. I think it's a really useful formula to memorize. You don't have to memorize it. I'll give that to you on the exam, so don't spend extra brain power trying to memorize this if you haven't already. You will need to memorize how many atoms are in each of the kinds of different cubic unit cells. So do spend some time doing that. Okay, great. We've got the volume of a sphere. We're treating these atoms like spheres. So for a face-centered cell, we have 4 atoms times volume of a sphere to get 16 pi r cubed over 3. Great. This is the volume of the atoms present in the unit cell. Now notice we still have a variable in this answer. We still have r. We don't have any definition for r yet. In this case, we don't really need to have a value for r. We're just looking for generic packing efficiency. It doesn't matter if we're dealing with carbon or with tin or with any other kind of atom. Hopefully at the very end, if we do everything correctly, r will cancel out. Okay? So just leaving this right now as r cubed is okay for calculating packing efficiency. Not a problem. We'll leave it that way. All right, moving on now. We've got this first number down. Now let's work on finding the volume of the unit cell. So I'm just going to draw a real quick sketch here. The cubic unit cell. Now I am not an artist, as you can tell already by this. All right, that's fine. Let's do this. Another reason why I didn't end up teaching geometry. Okay, here we go. All right, so here's a rough sketch just of a cubic metal cell. And in this case, of course, we're looking at a face-centered cell. I'm going to call each side of this cube A. I haven't drawn the atoms in here because that might clutter up my picture a little bit too much, but we'll look at the picture in just a second of how the atoms are arranged. Okay, here's the volume of my unit cell. Now, if you'll recall, the volume of a cube is simply equal to height times length times depth, or just the length of one side of a cube cubed. Volume of a cube is a cubed. Great. Now here's the problem. If I try to divide the volume of atoms by the volume of the cube I have right there, I've got two variables. It's not really going to work out well. So let's see if we can simplify this to actually get a numerical percentage. We totally can. If we can somehow get A in terms of R, then we'd be able to cancel out R and come up with some kind of percentage. So that's our challenge, is to write A in terms of R. So we need to think about the atomic structure, the way atoms are arranged now inside of this face-centered cubic metal. So I've got to pick up my iPad here so I can show this to you. All right, let's look at the picture here. Whoa, let's try that. There we go. All right, there's our face-centered cubic metal. So you can see we've got 1/8 of atoms on the side. We've got a 1/2 atom on the center there. And one thing you'll notice, oh, this is so shaky. I'm so sorry, you guys, because I'm holding it with my hand in this case. What you'll see here is that we could draw a line right on the face of this cube, and that line would be passing through atoms, okay, right along the radius of those atoms. So we could start maybe by using that line that we could draw there. We could start with that and see if we can come up with an expression now for A in terms of R. All right, so that's where we're going. That's where we're headed. Okay, so I'm going to kind of redraw what I was just talking about there. So we're going to highlight the face of this here. Okay, imagine that we're pulling this face out and we're superimposing the atoms that we saw in that PowerPoint picture on there. So let's redraw this here. This is one face of the cube. Right, it's this face here, we're just pulling out to here. All right, each side is labeled A, and I'm going to draw a line right along the face of that cube. There's my line. Okay. Now, this is really going to be out of scale, so forgive me. But remember what's going on here? We've got an atom here, and then we've got pieces of atoms. Oop, these are touching. That's important. Okay, pieces of atoms right there. And I'm just drawing a line through the radii here. So if I wanted to say something about this line here in terms of the radius that it's passing through, we could call from this point to this point, that's R. This point to this point is R, R, and R. So this whole side here, this whole hypotenuse that I've constructed of this triangle can be thought of as 4R. Great. So now I'm starting to be able to see the beginnings of some kind of relationship I could make between A and R. All right, here's the foundational piece. All right. Now, in order to come up with some expression where I can relate the two, it's important that we remember our trig functions in order to be able to do this. I like using trig functions for this. I just think it's kind of fun. And I like trig, so that's the way we're going to do it. So if you remember your trig functions, some people use SOHCAHTOA. I don't like SOHCAHTOA. I like Oscar and Oswald have had algebra. This is this is sine, cosine, and tangent. Cool. Now I could use sine or I could use cosine for this expression that I'm about to make. I'm just going to use cosine because what the heck, why not? Cosine is the adjacent side of a triangle, cosine of some angle, is the adjacent side of a triangle over the hypotenuse of the triangle. All right, so I can look at my adjacent side, which will be A, whichever angle I choose, and the hypotenuse. Using one of these angles, I can relate now A to 4R. Okay, using one of these angles, I can go from angle, relate A to R. Sweet. Now in order to do that, we need to know what the measurement is of each of these angles. So here we're bisecting 90 degrees when we're making this line. So each of these angles, I really need a third color, each of these angles is 45 degrees. All right, again, because we're bisecting a 90-degree angle here. This is 90 degrees. Okay, now I need to remember my trig functions here. The cosine of 45 degrees is equal to square root of 2 over 2. I'll go ahead and give you these trig functions on the exam, so don't worry about it. You don't need to go ahead and memorize all of these. Might not be a bad idea, just in general, but you don't need to memorize it. So the cosine of 45, square root of 2 over 2. We'll use this angle right here. Here's this one that I've labeled. Okay, so this is 45 degrees. Cosine of 45 is square root of 2 over 2 equals adjacent, which is A, over the hypotenuse, which is 4R. Oh, this is so exciting. Look, we're starting to make a relationship between A and R so we can plug it into here and cancel it out when we finally find our packing efficiency. Very exciting. Great. All right, so if we do some algebra magic, we can solve for A. A is 4R square root of 2 over 2, or 2R square root of 2. Great. So if that's what A is equal to, my volume of my unit cell now, A cubed, let's see, let's write down here, V unit cell, is equal to A cubed equal to 2R square root of 2 cubed. Sweet. Or we could, pull this out and do a little bit more algebra, and we could say it's 2 square root of 2 cubed R cubed. R cubed. Totally legit. We can do that. Now look, oh, this is so exciting. Look, now we've got R cubed in the volume of the unit cell. It's going to cancel out with R cubed in my volume of atoms. This is great. Okay, so now packing efficiency. I'm finally ready to calculate it. All right, so I take my volume of my atoms, 16 over 3 pi R cubed, divided by volume of my unit cell, 2 square root of 2 cubed R cubed. These cancel, so great, and I end up with 74% packing efficiency for a face-centered cubic metal.